We are now beginning part 2 of the regression, which is regression line through the origin. This is where beta naught is actually 0. So here sometimes a regression model with beta naught equal to 0 is desired, such that the assumed model is as follows: yi is equal to beta times xi plus epsilon I, of course, for I equal to 1 up to n observations. The model parameter can be estimated here. We are saying parameter because there is only one, which is beta. Note that it's not carrying any subscript. So it can be estimated using least squares technique. But bear in mind that the fitted regression equation takes the form y hat is equal to beta hat xi. As usual, we try to find the best fitted equation that minimizes the sums of squares of residuals. And hence, with those that equation over there, which I said before, we are no longer going to look into such rigorous mathematical issues. So as we move down, we end up with the beta hat equal to sum of xi yi over sum of x squared. Note the changes here. We are no longer having sum of xi yi minus nx bar. We no longer have that. So we have sum of xi yi over sum of x squared. Then hypothesis test involving beta, with beta is equal to b and beta is not equal to b, a two-tailed test. And the test statistics beta hat minus b over s, of course, divided by root of sum of x squared. This is now distributed as t, but with n minus 1 degrees of freedom. The degrees of freedom have changed in this particular case. Of course, we will reject h naught if the absolute value of t is greater than the critical value. So let's look at how do we calculate the sums of squares there. Total sums of squares is now just sum of yi squared, while regression sums of squares is beta hat times summation of xi yi. SSE is found by subtraction as usual. I will look at the degrees of freedom. Regression df is remained 1, but the error degrees of freedom here, the error degrees of freedom is now n minus 1. The total degrees of freedom is now n. The other mean square errors is found using the usual way, where you are dividing SSE by its corresponding degrees of freedom, as well as MSR is found by dividing SSR by its corresponding degree of freedom there. F naught is found the usual way. This is regression through the origin. Just take note of the changes in the formula for SST naught and for SSR, and the rest of the stuff remains the same. Also, the test statistic for testing that single parameter is changed. Now, how do we check the model parameters which we discussed in part 1? The first step is to check the linear assumption is to construct a scatter plot of the data. In this case, we are checking linearity between y versus x. If the graph is a straight line or almost straight, then the assumption is not violated. Another way is to calculate the correlation coefficient. If assumption is not violated, then the correlation of x and y should be close to 1 or to minus 1, showing a very strong linear relationship existing between y and x. So it should be close to 1 or to minus 1, where we have an inverse relationship. The graph below shows an example of a bad linear relationship. Most points are not on the line. If you look at this graph here, you realize that most points, except those two, are not on the line. So this is not a very good linear relationship between x and y. We also look at normality. There are many ways to test for normality of residuals. We use QQ plots or the so-called quantile plots. We can also use histogram of residuals. We can also use the Shapiro-Wilk test and the Anderson-Darling test. Right? The QQ plots, these are plots of ordered residuals versus the normal distribution quantiles QJ, which are defined by probability of Z less or equal to QJ is equal to J minus 0.5 over N. Note that we've covered these aspects before. You might use R to do a QQ plot by simply using QQ norm, and then you fit a line using QQ line. And the resulting plot should actually be a straight line if the numerical assumption is not violated, which means there should be a linear relationship there between QJ and the ordered Ri. The other way to check formality is to use the residuals. A histogram of residuals should be bell-shaped if the numerical assumption is not violated. Let's look at the other stuff here, coefficient of determination, which is R squared. R squared is a measure of fit of the regression line. It represents the proportion of variation in the response data that is explained by the model. So the quantity takes values between 0 and 1. Of course, a very good model would have an R squared around 90-something%. If the fit is perfect, R squared is equal to 1 and all the residuals are equal to 0. And if that scenario is when the fit is very perfect. R squared is actually given by the sums of squares or regression over the total variability, which is sst0. You may multiply that by 100% if you want it in percentage form. Disadvantages of using R squared as a measure of the quality of fitted model. Not a good tool for model comparisons because any additional model terms, which means addition of another independent variable to the model, will simply decrease sums of squares for error and thus increase R squared. Overfitting may increase R squared unnecessarily. Now, an increase in R squared does not imply that the additional added term is actually needed. R squared can be artificially high either if the slope is large or if the spread of the regressor data is large. So in other words, you have to use R squared with caution as a means of checking the adequacy of the model. Okay, let's look at the general steps in regression. Construct a scatter plot first. This is you want to examine the graph closely. You want to see whether or not there is a linear relationship existing between the dependent and the independent variable. Now, depending on the plot, you may transform the y or the x or y variable so that there is a linear relationship between the two. That's the first thing that you have to do. Check for linearity, right? And if there's need for transformation, you might transform the variables. You then calculate the linear regression statistics, the fitted equation, R squared, parameter estimates, and the ANOVA table. Next, you examine the regression slope and the intercept. Does the regression equation predict reasonable values of y? You then have to do residual analysis to see if the plot and everything else, the fitted model was okay based on the data that is given. Let's look at correlation. Correlation between two variables is a measure of the strength between them. While the covariance tells us whether or not a relationship exists between variables, it is the correlation actually that defines the strength of such a relationship. And if the population correlation coefficient they are given, we hardly use that. We use normally the sample correlation coefficient. Rarely do we find population data. The value of the correlation coefficient is between -1 and 1 with the following interpretations. Of course, if rho of xy is equal to 1, then xy are perfectly positively linearly correlated. In short, it means y is increasing at the same rate as x. Now, if rho of xy is equal to -1, then x and y are perfectly negatively linearly correlated, meaning one variable is increasing as at the same rate as the other variable is decreasing. That gives a correlation coefficient of -1 there. Then if rho of xy equal to 0, it means that there is no linear relationship existing between the two. If rho of xy is greater than 0, x and y are positively linear correlated. If it is less than 0, these are negatively linear correlated. Then this is the formula for evaluating the correlation coefficient. But if you have a calculator, there is no need for you to know this formula because our calculators are designed to calculate the correlation coefficient. We then have finally the correlation test. This is a statistical test to test if the correlation coefficient actually is equal to 0 there. Step 1 is the hypothesis. Step 2 is the test statistic. T is equal to R root of n minus 2 there over 1 minus R squared. This is as a T distribution with n minus 2 degrees of freedom. Then, of course, the decision, you reject H0 if the absolute value of T is greater than the critical value. And of course, you can make appropriate conclusions based on your decision. I can say in a nutshell, this is it about the second part of lecture 8 that looks at 1, a regression through the origin, and 2, the correlation coefficient, as well as the correlation test, which we have done there. So at this point, I will say this is all about regression. But what you need to understand later is that we will need to do these things using R.